Thank you again for taking this course, Java Programming on the intermediate level, a presentation of coding boot camps. In this session, session 2, we are going to discuss fundamental data structures. So here is our outline. First, we are going to look at dynamic memory allocation. Then we're going to look at linked list, stacks, queues, and trees. So dynamic memory allocation is not so much a data structure, it's how memory is managed, and this is true for many object-oriented programs or programming languages. All Java objects are dynamically allocated, meaning memory is reserved for them at the time it is needed. So we're passing around references to objects, and this is how the Java language was designed. So when we declare or instantiate class A here and store it in OBJ, what we are doing is creating memory for this class A, but pointing back to the name OBJ. What happens here with the object, space is allocated on the heap and a reference is stored on the stack. So object and the class A version of object, class A is on the heap with object on the stack, and they are pointing to one another. So what this means is that we can always pass objects without worrying about where they are stored. So in Java, linked lists, they implement an interface called the list interface, and you can go back and take a look at all of the methods that are used for the list interface. Both arrays and linked lists can be used to store linear data of similar types, and they both have advantages and disadvantages over another. So the following here are points again in favor of linked lists. So with an array is considered to be of fixed length. We know the upper limit because when we declare it, we're declaring what the upper limit is. So we know those the numbers and the elements in advance. Also, the allocated memory is equal to the upper limit, as you would expect. In a lot of practical uses, the upper limit is rarely reached. Inserting an element in an array is quite expensive because of the room that has to be created for the new elements, and to create existing elements, the current elements have to be shifted, which is also an expensive process. So if we take a look at this example here, so we have an array here of a number of IDs, and we can see that they are sorted. If we want to now insert a new element and keep the list sorted, we'd have to put it in here into the first index of the array, and we'd have to move over the actual memory and then restore all of the other IDs. So that is that's expensive as far as reordering all of the values. Deletion is also expensive with arrays. For example, so to delete 110, everything then would have to be moved again. So dynamic work or any kind of dynamic calls with an array is an expensive process. But linked lists provide two advantages over arrays: dynamic sizing and the ease of insertion and deletion. So we don't have to know the upper limits of a linked list. We can grow a linked list dynamically, or we can delete it dynamically, or delete from it dynamically. The list class consists of several methods. We have we have one overloaded add method, and we also have add first, add last, and contains. With the overloaded add methods, we can call add and just pass in one element, and it appends an element to the end of the list. We also have the add here where we have to pass in an index, and an element, and it inserts the element at the position of the index that we're passing in. Add first inserts a value or an element at the beginning of the list, so it's a variation of add, and then we have another variation of add here again where we add last. It appends the element to the end of the list. And contains returns a true or false, and it returns a true if the element is present in the list. And take a look at this Java application or Java program or Java class here, class test, and here's our main method. We're instantiating a linked list. We're calling it object, and we're calling add. We're calling add last, add first, and we're getting some output. Then we're calling remove, and we're getting some output, and we're calling contains, and then we are getting some output and testing some output. So this is a good example, so try and key this in as much as possible and get a real understanding of how the linked list works, the methods work, and take a look at the output. So stacks is another data structure, and it is again, it's a collection of values, collection of elements. However, a stack uses the last in, first out, or LIFO principle. So the pointer of a stack is always pointing to the top of the stack. When a stack is first created, it's empty. So what's added to the stack, that last in or most recent in, that pointer is going to be pointing to the top of the stack. So that element or that value is on the top of the stack, it will be selected first. Stack is a subclass of vector, and vector implements a standard last in, first out. The stack only defines a default constructor, which creates, again, that empty stack. The stack includes all the methods defined by vector, but adds several of its own. So anything that we push on to the stack will be the first to what we call be popped off. The methods of the stack class, empty, so this returns a Boolean. It returns test to whether the stack is empty, returns true if the stack is empty, and returns false if the stack contains elements. Peek returns the element on the top of the stack but does not remove it. Pop returns the element on the top of the stack, but it removes it from the stack. The push pushes the element onto the stack, and also that element is returned. And search searches for the element in the stack. If found, its offset from the top of the stack is returned. So that notice its offset is returned. So how many positions down that element is from the top of the stack. Here is a Java class or a Java application. Here this class is stack demo, and you can see we have our main method, and we're also importing the Java utility classes, and we have a show push where we are pushing elements onto a stack, and we have a show pop where we are popping. We're calling pop on the stack and returning that information. So if we look in our main method here, we have our stack. We're instantiating stack st, and we're getting some output. And here we're calling show push on stack, and you can see the elements. And we are calling show pop on the stack. And we also, of course, have the try catches as well. And we have a try it here, so you can go ahead and key this in and run through it a few times. It's a great way to get comfortable with how the stack data structure works. A queue is another data structure. There is a queue interface, and a queue is an ordered list of objects, and it has limits as far as inserting, because we can only insert elements at the end of the list. and we delete elements from the start of the list. So it follows the first in, first out principle, or the FIFO principle. And again, a queue is built from an interface, so it must be declared from that interface, and there are many ways to utilize the queue object. The most common way to utilize a queue is something called a priority queue, and then as a linked list, and we'll see some examples of this. Here's another example of a Java application or a Java class for a queue. This class is queueExample, and we have our main method here, and we see here we're importing the Java utility linked list and queue. And if we take a look here, we are instantiating queue as a new linked list. So you can see here it's we're instantiating a new linked list of type queue. Then we're going through here, taking our queue object, and we are adding these elements to it. We're just counting up here from 0. We're counting up 5 times. We are displaying the contents of the queue, and then we're removing the head of the queue by calling remove there, and we can get some output. And again, we are taking a look here at the elements, and just so you can get some work with this. This is really good. We're viewing the head of the queue here by calling peek on queue, and we're getting some output here. And then we are going through where we rest all the methods of the collection interface, like size and contains can be used with this, but we're calling size here and getting some output. So this is a really good example. So take a look through it if you want to. Go ahead and key it in and run it a few times, and you'll get a good understanding and a great exercise with queues. A tree is another data structure, and interestingly enough, we probably use trees every day without even realizing it, using the tree data structure. All of our file systems that are on either our laptops, our computers, our MacBooks, and so on, our file systems are all in trees. So in the case of Windows, we could have the C drive, which would be the root of the tree, and then all of the folders and files and subfolders, they are all the branches or the leaves of the trees. So it's a data structure that, even though we don't hear a lot about it, we do use it more than we realize. So formally, a tree is a nonlinear data structure where the data objects are organized hierarchically. The structure is nonlinear in the sense it's not like a simple array or linked list. Data in the tree is again organized in that hierarchical fashion, and each element is stored in a structure called a node. The topmost starting node and a tree is like an inverted tree, like we think of live trees with the roots in the ground, but in this case it's inverted. So the top of the tree is the root node, and all nodes are linked back hierarchically to that root node. So that would be similar to our C drives. Our C drives are the root of our file system trees, and from there all of the files and folders are those hierarchical subtrees that are pointing back to that root node. So that's a good way to understand trees. A tree data structure is useful on occasions where the linear representation of data does not suffice, such as creating maybe a family tree. Java provides 2 built-in classes, tree set and tree map. So we can, if we instantiate these, we will be able to insert data into Java trees. And also from this, take away how your file system on your computer expanded a little bit, and take a look at the tree data structure. It's a really good way to visualize it and get a great understanding of how it works. And again, here is a Java class, which is a good example of how to work with the trees. Here we're importing the Java utils libraries for arrays, a sorted set, and a tree set. The class is called tree set demo, and here is our main method. So here we're declaring an integer array called nums, and we're adding in our values, and then we're instantiating tree set. We're calling it tree, and we are passing in our array called nums. You can see it here, and then we are just calling some output tree. We're calling the first method, the last method on tree. Here you could see we're adding, we're calling the add and add one, and so take a look at that. We're calling on tree, we're calling add again in 11, and then we're doing print all tree. And then we're calling print all tree headset, and we're passing in the 7 there. And also take a look here at this method, print all. So this is a great way to get comfortable with adding trees to your applications. A really good example. So if you want to go ahead and key it in and run it, it's a great way to learn more about trees. So just to summarize what we learned, we discussed dynamic memory allocation, linked list, stacks, queues, and trees. In our next session, we will be discussing exception handling. So we'll look at types of exceptions, exception overviews, exception class hierarchy, extending exception classes, and when to throw or assert an exception. And again, please consult your learning materials on private tutoring sessions and coaching sessions for Java programming and for other training. And again, thank you for watching this video on intermediate Java programming. And this has been a presentation of Coding Bootcamps.